Good morning, everybody. Today we have a Codeforces round. This is Codeforces round 766. As usual, we'll have the screencast in the beginning, and at the end of the contest, we'll have solutions to all the problems I know how to solve. So I haven't read any of the problems yet. We're going to jump in. We're going to start exactly 5 minutes late. Without further ado, here we go. All right, we have a grid of n rows and n columns. Some cells are black, the rest are white. In one operation, we can select some black cell and do one of the following. Color all the cells in its row black or all the cells in its column black. Okay. We're given two integers r and c. Find the minimum number of operations required to make the cell in row r and column c black, or determine that it's impossible. At the very least, we can do a BFS. We could also do it in two moves always, if there's at least one black cell. Otherwise, we can do it in one move, maybe. Yeah, okay. So that's the idea. So let's do that. I destroyed my template. Interesting. Anyway, all right, so we have the number of rows and the number of columns, right? Oh wait, what is n and m? N and m are height and width, and then we have the cell of interest. Okay, int height equals this, width equals this, y equals this, x equals this. And we have char board, new char array height by something equals 0, y is less than height, y plus plus, and board at y equals next line. Oh yeah. Right. So then it can be black, right? All right, so then we want check if it's 1. So if board at yy, this x, man, voice crack equals this b, that means it's just 1. And we'll do a similar thing with y's. Y's up to height. Okay. Otherwise, we need to check if it's 2. Is this out 2? Oh, this needs to be outer. Okay, and then otherwise it's impossible. Looks plausible. Nice, we got it, All right, let's move on to problem B here real quick. And fix my template. What have I done wrong? Oh, this. That's annoying, okay. All right, Rahul and Tina are looking forward to their new year at college. As they enter their new classroom, they observe seats of students arranged in an m by m grid. Yet again, the seat in row R, column C is denoted by RC. The distance between two seats is their Manhattan distance. As class president, Tina has access to exactly k buckets of pink paint. The following process occurs. First, Tina chooses exactly k seats in the classroom with the help of pink paint. What? With the, oh, in the classroom to paint with pink paint. Where did I read the word help? I'm just going crazy. All right, 1 bucket of paint can paint 1 seat. After Tina has painted K seats in the previous step, Raul chooses where he sits. He will not choose a seat that's painted pink. Okay. After Raul has chosen his seat, Tina chooses a seat for herself. She can choose any of the seats, painted or not, other than the one chosen by Raul. Okay. Raul wants to choose a seat such that he sits as close to Tina as possible. However, Tina wants to sit as far away from Raul as possible due to some complicated relationship history that couldn't fit into this statement. Now, Raul wonders for k equals 0 to n minus 1. If Tina has this many buckets of paint, how close can Raul sit to Tina if both Raul and Tina are aware of each other's intentions and they both choose seats as strategically as possible? Gotcha. So Tina's always going to sit in the corner. Wait, what? If Tina painted these, oh, because Raul will pick someone, then Tina will go to the farthest corner. That's interesting. Yeah, yeah. Okay, so the pink paint just determines where Raul can't sit. So Raul does have a score for every seat. Yeah. And then Tina will paint the best ones first, and then Raul has like a worse and worse and worse score. Yeah, yeah. Okay. So it's not actually that hard to do. Yeah, so every seat has a fixed score because the pink doesn't change the score. Because Raul will still walk. Like, even though this makes it look like he has to walk around, he can just walk directly towards Tina. And then Tina will just paint the best ones first. Sounds good. Yeah. Good. All right, so int height equals this, width equals this. Int x equals 0, less than width, x plus plus. Y equals 0, y less than height, y plus plus. Priority q, integer q. Well, yeah, priority q. This works, I guess. So int dist equals x plus y. Dist equals math.max of dist and width minus x plus y. Plus height minus y. And then we also need x plus height minus y. This should be minus 1, this should be minus 1, and this should be minus 2. Cancel. All right, and then well not pq dot is empty, sys out pq dot remove. Is this right? Surely. Oh, pq.addDist. Three, a bunch of 4s, 4 5s, 1 1. Looks good to me. Let's move on to C. We'll let our lights tell us how we did. We have a tree of n vertices numbered 1 to n with edges numbered from 1 to n. Okay, we got it. A tree is a connected, undirected graph without cycles. We have to assign integer weights to each edge of the tree such that the resulting graph is a prime tree. A prime tree is a tree where the weight of every path consisting of 1 or 2 edges is prime. That's going to be a problem. You have to assign integer weights to each edge of the tree such that the resulting graph is a prime tree. Okay, 1 or 2 edges is tricky. A path should not visit any vertex twice. The weight of a path is the sum of edge weights in the path. Yeah. So we're going to run into even problems. We can use 2, but that's about it. Okay. Consider the graph below. It is a prime tree as the weight of every path is of 2 or fewer edges is prime. 7, 2, 5, 11. Yeah, so we can use only twin primes in 2. Yeah, everything's got to be a twin prime in 2. Print any valid assignment of weights that the resulting tree is a prime tree. Can we make everything just 1 and 2? Can we reuse stuff? Do they have to be unique? Surely it's always possible, right? You just use 2 and 3 for everything. Second case is described in a statement. Oh, what about the third case? This should be fine. Okay, this is a tree, right? We could 2-color it if we wanted. Oh wait, can we not? This might be a problem here. Yeah, this is a problem. So if you go like 2, then this has to be a 3. This has to be both at the same time. Yeah, so you can't have any node with degree 3. If you don't, you can just color the whole thing. Yeah, okay, we got it. That's the solution. Let's code it. What do you say? So we have n, right, we have, yeah, n and then the edges, okay. We need edge classes. Yeah, darn. Static class edge. Int from to, we probably don't need nodes then. These aren't actually the nodes though. These are, or the edges, these are the nodes. And we'll have an edge array edges, new edge array -1. So I equals 1 less than n I plus edges at I minus, well, all right, so yeah, we've got this. All right, so now, is it impossible? So for int I equals 0 less than n plus plus, if nodes at I dot size is greater than 2, sys out -1, and then continue outer. This is going to need to be print writer. All right, here's our outer loop. Looks good. So we've got this. Man, am I destroying this microphone here? Hopefully that's better. Sorry if the audio quality is terrible. Okay. Yeah, man, it's still quite loud. Maybe that's better. All right. Oops. Live and learn. Okay, so yeah. Handles this case. Next, we need to just paint it, right? So twin primes 2 and 3, and then we'll go through all the nodes. So if nodes at I dot size equals 1, then endpoint equals I. All right, so then array, oh, we need the list of edges, huh? Int, yeah, so add is just endpoint. All right, so if edges at endpoint, or sorry, nodes at endpoint dot get, or dot is first just a method, dot get 0. This equals from, then from equals get 1. Oh, so if nodes at endpoint dot size equals 1, then break. All right, otherwise get this, otherwise get 0, and then endpoint equals nodes, or equals end, okay, endpoint XOR equals nodes at endpoint dot from, oh, from dot from XOR from dot 2. All right, so flip which one we're at, do this, and then add this to the list. Keep going, okay. For int I equals 0 less than edges sorted at size I plus plus. So this color is going to be 2 plus I mod 2. All right, and then for int I equals 0 less than n minus 1 I plus plus out dot print edges sorted dot get I, or just edges at I dot color plus a space and then out dot print line. Should be good here. That could not possibly be 0. Yes, it can be. So nodes at edges at I minus 1 dot from dot add edges minus 1. This should be fine. So this is 1 this 0, 2. Oh. Okay. Yeah, that's good. All right. How are we doing? Not too bad, actually, honestly. All right, problem D. We have an array of n distinct integers. We can perform the following operation on it. Choose 2 elements of the array such that the GCD of these elements are not present and add the GCD to the end. Note that the array changes after each operation and subsequent operations are performed on the new array. What is the maximum number of times we can perform this operation on the array? We can only do it if the GCD isn't present. Got it. I see. Choose 2 elements. They can be any 2. Okay. So we might as well sort it, right? Doesn't hurt. So what is an upper bound on this? It's not going to be that big, right? So we can have like at most we've got like, yeah, for each element, this thing can be decreased to at most cube root. Which is kind of a lot. Yeah, cube root n is kind of big. But like we can't have cube root n different things. Like at most, like GCD is not going to get bigger, right? So at most we have 10 to the 6 things we can hit. So it's not going to be terrible. Should be able to handle it eventually. Okay, so how do we do it? Well, how do we find what we can hit? Go through the factors of each number. There are a lot of those. There aren't that many. I don't think there are that many. Most things probably don't have more than 100 factors. Probably fewer than 10 to the 8. All right, so we go through all the factors of each thing, and we're like, can we hit it? Is there like a really easy BFS way of doing this? We need to know, like, yeah, so you've got a bunch of different primes here. Got like 2, 3, 5, 7, 6 is not prime, 7, and like 11. So one of the numbers will handle like 3 of these, the other might handle the other 2. We need together, we need every number to be handled for you to be able to be reached. I wonder how many prime factors a thing can have. Probably not that many. 2 times 3 times 5 times 7 times 11 times 13. So 13, so we can get 2, 3, 5, 7, 11, 13. That's only 32, okay? The next prime after 13 is 17. Okay, we can get 17, but we can't get more. So this is 1, 2, 3, 4, 5, 6, 7. 2 to the 7 is 32 times 4. Should know this. 128. Yeah, okay, not terrible. So, what is this saying? For each element, well, actually, we're not done with this yet. All right, so we have at most 7 prime factors per number. This is going to be very tricky though, because we're going to wind up with hash maps probably. That's what it's looking like. So there are 2 to the 7 bit masks to keep. For each one of these bit masks, so it'll be like you keep these numbers. Oh, but then you can only use things which match with your other things. So it's like if you ignore these, what else can you reach with one number besides you? But it's only a submask of these 7 prime, or of these 7 things. Okay, so maybe this is not the right approach. What if instead we have like some number like 5 and then some number like 15, and we're at 15 and we're like, okay, can we get to 5? So what else do we need? Right, what do we need here? We need something else that includes a 5 but not a 3. So it has to have 5, but not 15. Yeah, so we'll count, yeah, we want to count the number of things with 5 as factor and with 15 as factor. Okay, if we have 5 as a factor, we have 15 as the factor, then we'll get what we're looking for, right? Yeah, and then we need more 15s than 5s. So we need like a count of how many of each factor there are. Or count of number of times that x is a factor. And then we process this from biggest to smallest. I think that handles it. Do we need big to small even? I don't think that part even matters. Yeah. Okay, let's do it as an example. So we have 6, 10, 15. So 6, we hit 2, 3, I guess we hit 1, and 6. All right, 10. Can't make any of these. 10. We hit 1, 2, 5, and 10. So can we hit 1? Yeah, to hit 1, you need, oh wait, how do you hit 1? No, let's just add, every time we add something, let's just add to the end of the list. Okay, so we're only going to be removing, oh wait, but we can remove multiple things. Okay, good thing I tried this. So for the 10, we have a couple problems. Like, so what were we trying to figure out before? This 15 and 5 works well. It has to have the 5, but not any other factors for us to use it. For this, okay, to include the 2, it's easy. It's got to have the 2, but not the 5. To have the 1, has to have the 1, but it also can't have the 2, also can't have the 5, but has to have the 10. So this is inclusion, exclusion. Plus, minus, minus, plus. Yeah, but like, Geothermal's a wizard. So quick. Well done, sir. 5 minutes. Speedy. All right. If we have, yeah. Let's read E. Major Ram is being chased by his arch enemy, Raghav. Ram must reach the top of the building to escape via helicopter. The building, however, is on fire. Ram must choose an optimal path to reach the top of the building to lose the minimum amount of health. The building consists of n floors with m rooms each. Let this represent this room with this floor. Additionally, there are k ladders installed. The ith ladder lets you go from this place to this place, but not in the other direction. Okay, this is a very poorly written problem, but I'll deal with it. Ram also has this many health points. If he uses this ladder, it is guaranteed, what? He gains this many health points if he uses this ladder. It is guaranteed AI is greater than CI for all ladders. So ladders only go up. Okay, got it. Got it, all right. If he's on the ith floor, he can move either left or right. Traveling across floors, however, is treacherous. If he travels from I to J, he loses from IJ to IK, he loses this many health points. Okay, so you lose X health points every time you move left or right. But that differs between floors. Okay. He enters the building at 1-1 while the helicopter is waiting at NM. What is the minimum amount of health Ram loses if he takes the most optimal path? Note this answer may be negative, in which case he gains health. Okay. All right, what? So we have this building. We have some ladders that go up, but they can go left or right. We're trying to escape to get to the top. You can only take ladders up. Yeah, okay. So how many ladders can there be? Number of ladders respectively. Yeah, so you kind of just have a graph. Right, you just have a graph and then you run Dijkstra's. There are no negative cycles. You can have negative edge weights. Yeah, but just prioritize being on the lower floor. So this is just a graph problem. Okay, this is a terrible problem. Honestly, this is like one of my least favorite problems I've ever solved. It's easy though. I don't know why people aren't getting it. It's definitely easier than D. Somehow worth more points. All right, yeah, I guess we'll just solve E. Yeah, okay. Fine. The number of floors, the number of rooms on each floor, and the number of letters. Okay. All right, so int low equals, or low, and then high, and then health. Oh, we also need the start x and end x. Yeah. Okay. Not helpful. Okay, these are the costs. Yeah, so then all right, so what's next? We have k lines, so tight time limit? No, it's fine. So this is A and B are start Y, start X. Yeah, all right. So low int SX, high int end Y. Oh, end X. Yeah, okay, so we've got this, that's fine. Where does he start? 1, 1. All right. I guess we might as well choose a hash map. All right, so node needs a int floor, int x, long distance equals long dot max value over 2, and then that's it. So public node int floor int x implements comparable node, I guess. Dot floor equals floor dot x equals x. All right, cool. So we've got this. What next? Edges. So this is node from, node to, long cost. All right, that's fine. Okay, what about the state? We need a node at, we need a long cost, and that's it. So if at.floor is not equal to o.at.floor, return integer.compare at.floor, o.at.floor, return integer, or return long.compare cost to o.cost. Okay, nice. So now we need yeah, okay. Floor, and then int x, and then public node get next, int floor int x. I guess we only need one way, right? Yeah. All right, so if all, okay, so node test equals new node floor x. And then node seal equals all nodes. Okay, if seal is not equal to null and it fits, then return it. Otherwise, all nodes.add test and return test. Okay, so this is almost the same thing. If test, yeah, okay, so if seal equals null, then return null. If it's not, that means we need to check the floor. So if seal.floor equals test.floor, then return seal, otherwise return null. Yeah, okay. So start will be get 0, 0. Then we've got all nodes.clear. Cool, and they said we can end at any height, right? Okay. And then we need each of the ladders. So then, I guess we go through each ladder. So for int I I equals 0, less than n ladders, I plus plus. We're given, okay, so ladder test equals new ladder. So these are all 1 indexed. Okay, so then, let's call it L. What now? Now we need to add this edge. So node from equals get L dot low L dot SX. And then 2 equals get L dot high L dot NX. From dot edges. We should be good there. Okay, so we add these. Awesome. Yeah, I think we're fine then. Okay, nice. So then, for node nn in all nodes, if nn dot floor equals h minus 1, then break. Otherwise, node next equals nn or equals all nodes dot higher nn. If next equals null or next dot floor is not equal to nn dot floor, then continue. Otherwise, int dist equals yeah, so then, okay, so nn dot edges dot add new edge from nn to next. The distance is simply move cost at x at nn dot floor times next dot x minus nn dot x. And we can also go backwards. Yeah, okay. All right. So now we need our Dijkstra's. Okay. So the state just has which node you're at and the cost. So start and 0, and start dot cost, start dot distance equals 0. I think that's right. So then while not pq dot is empty, state cur state equals pq dot remove. If cur state dot cost is not equal to cur state dot at dot dist, then continue. Otherwise, for edge EE in cur state dot at dot edges, long new cost equals EE dot cost plus cur state dot cost. So if new cost is less than EE dot 2 dot distance, then EE dot 2 dot distance equals new cost, and then EQ dot add new state to E dot 2. The new distance will be new cost. Should be fine then. Okay, so then long answer equals long dot max value over 2. Sys out ans greater than or equal to long dot max over 2. If it is, print -1, otherwise print answer. Okay, so this keeps running good, and then for node nn in ends, if this distance is less than answer, yeah, I guess we just say answer equals math.min of answer in nn dot distance. Should be good there. What does this give us? Literally no escape. That's annoying. Oh, we're getting some things wrong. Okay. This is just a terrible problem. This is like almost downvote the contest level of a bad problem. Okay. You're telling me this first one is 8. First test case is in the statement. There are only 3 letters. Oh, this is this thing, okay. So we get 4 health, 5 health, or 6 health. All right, let's look at the first case then. So we have 5 rooms. 1, 2, 3, 4, and 5. Their costs are $5, 17, 8, 1, and 4. Okay. So first of all, we have one going from 1 3 wide. Okay. So 1, 3 to 3, 3. This is -$4. Okay. Then we have 3, 1 to 5, 2. This costs -$5. And we have this to this, which costs -$6. Okay, so we have to pay 10 here, and then we have to pay another 10 here. Oh, 10 for this part. Okay, so $10, we get 4 back, and we pay an $8. And then we go here, and we get 6. So the answer is going to be 18 minus 10. Surely, right? Pay 10, pay this, we get the 10. The answer is 8, isn't it? Why is the answer not 8? Tell me the answer is 16. Minus H1. So you get the 10, keep the 4, Pay for the 8. You get the 6. What is this 4 plus 2? Oh, you have to go to the top right. It's kind of silly. Okay. Oh. Ugh. This is like the most stupid problem I've ever seen on Codeforces in a very long time. Wrong answer. I know, running. Yeah, that was so dumb. That was insanely dumb. Ugh, what a terrible problem. What a horrendous problem. Just not a good problem. Not interesting, not fun, just bad problem. Oh well. Okay, we have a k by k grid where k is even. The square in row R, column C is noted by RC. Two squares are adjacent if they're adjacent. Okay. An array of adjacent pairs of squares is called strong if it's possible to cut the grid along grid lines into two connected congruent pieces. Oh man, look at that. It's kind of cool. Such that each pair is part of the same piece. Two pairs are congruent if one can be matched by translation, rotation, or reflection, or a combination. Okay. Let's see. You're given an array of n pairs of adjacent squares. Wait, what happens? Two squares are considered adjacent. Okay, we're given an array, of n pairs of adjacent squares. Okay, find the size of the largest strong subsequence of A. So wait, what is it? An array is strong if you can make two congruent things. Okay, I see. We want to find the size of the largest strong subsequence in A. An array P is a subsequence of A if P can be obtained by deleting several elements. What is K? K is small. This doesn't seem that hard. Seems easier than D as well. Be right back. So observation 1 is that no one of those pieces can have 3 of the 4 corners. Right? Like you can't have A has, like if the pieces A and B, you can't have this have these 3 pieces. Because like, I think at best you have something like this, but you just can't fit another one of those things in this square because it'll overlap it at some corners. So that's not going to happen. Additionally, if you have like a square, you can't have both of these corners because that means the other one would need these corners and these overlap. So that's not possible. So that means you have either you have A, B, B, or you have the other way, which is just A, B, B. And these are, oops, these are literally the only 2 ways of doing it. Okay, so if you have it like this, if you have a reflection, if you have a reflection, then that means you have 2 rectangles, right? So you might as well always just have a rotation. So yeah, there's not really much use to considering anything other than a rotation. These bounds are kind of big. Wait, but there aren't that many unique bounds. There are only 4, there are only 4 times L4K squared. Okay, never mind. Wait, what is 500 squared? It's a big number? Okay. Got to be a better way of doing this. I don't know what it, there it is. There's a better way of doing it. Okay. Yeah, so when you've got some grid, you can't have any piece connected to, we can just do a 2-pointer sweep, right? Yeah, probably. The issue is, like, the problem with this 2-pointer sweep is we might have things like this, where it's like, where like this and this are technically disjoint, but not, we can't connect them. Maybe this doesn't happen though. Or maybe like if this happens, we'll be wrong for another reason. They have a nice good sample. Not really. So this is even here. It's always k by k. Yes, it's even by even. So these two are in the same piece. And then also, if we rotate it, these two are in the same piece. And then they're both in different pieces. Yeah, I guess we just need to make sure nothing's in the same thing as itself reversed. So what's the question here? The question is it possible to split something up into two groups without okay. Can you feel the well, it's just things connected to this, right? Everything else is just a connected component. Yeah. Like these things might be, we might have like some big group like this that's all connected. And then we have some analogous group like this that's all connected. But then if these things are just connected, right, that doesn't mean anything because we don't care which part they're part of. Yeah. This seems like a really easy problem. So it's like, yeah, okay, so I guess let's check the other, so I need to check the other part of it. So the question is like, would joining A and B create a cycle? Oh, I see why it's hard. Yeah, because you can't just like remove edges from a disjoint set. Yeah. Oof. This is possible with link cut trees. So we need a disjoint set. Oh, we just need like a suffix of edge. Oh, maybe this isn't hard. Yeah, this is cool. Man, how do you go from such a trash, garbage problem E to such a cool problem F? So, yeah, this is actually neat. So you can do it with linked cut trees, which I guess makes the problem less cool. But also you can say like, let's have like we need a suffix of or we need like a continuous range of operations. And root n. Yeah, you do. It's n root n. Can we do an n log n? It's cleaner to implement as well. It's got to be something like, for some positions, yeah, we merge these two. Maybe a link cut tree is just easier. So like we have an array of like, yeah, just unions. And the question is like, if we do these unions, does it connect the top left to the bottom right? Okay. Can you easily do this with, okay, we have 28 minutes left. Can we do this without link cut trees? We need some sort of like, something mildly smart. You can't really combine two disjoint sets. Is it really link cut trees? Ah. Okay. Link cut trees for the win. So how many people are solving this? 26? We can do it. All right. So we need like minimal, or I guess maximal spanning tree. We need the maximum spanning tree. Yeah. So we need to query path min. Yep, and then I guess this isn't hard. Query path min, remove it. If necessary. Okay. It's been a minute since I've used some link cut tree code. So yeah, what problem is this? This is problem F. Probably don't need these to be in this class. All right, we need this, and we need splay tree. Okay. Static class splay. Okay, what is the data? The data is literally just a number. We don't need the sum, but we do need the min or the max. We need the min. Yeah. We need it to be a node. I guess we can probably just do an integer. What is behead? Yeah, how do I not have behead? Where's behead? Okay. Man, that was easy. All right. How much time do we have left now? 20 minutes. It's gonna be tricky. Gonna be tricky. Okay. So, yeah, I should be fine. All right. Int n and then k. So this is side length. All right, so we need one thing for each node, right? Okay, so and then how many edges do we have? We want then one edge for each, or two edges for each query. So this would be side length times side length plus, how many queries? What is n? Oh, plus n times 2. Okay, so 4 equals 0 less than side length, 5 plus plus, and j equals 0 less than side length, j plus plus. Display nodes at I times side length plus j equals new display node. And the data will be a very large value, integer dot max value over 2. Let's just say int 1e9. All right. We'll say, yeah, row major order of the grid. Okay, so now we need all of the things. We need all of the things. I sound like I should be running for president, don't I? All of them, every last one. Let's get the input first. Yeah. This will be n by 4. Read array says 4. Okay, so now we have all of our commands. All right. So now the question is, yeah, I guess we'll have an L and an R. Right, so for int rightmost command equals 0, rightmost command is greater than or equal to, or is less than n, rightmost command plus plus. So now for the fun Yeah. So static All right, and then we need static void rotate. So some point P and then in width in height. Okay. So return new point. So what does this look like? So your X was here. Yeah, so the new Y is going to be width minus 1 minus P dot X. And the new X oh wait, is it 180-degree rotation? What is a 90-degree rotation? That's not going to work. Yeah, it's got to be 180. So you just flip both of these, right? Yeah, I think this is fine. Okay. All right. Fine. Okay, so we get this command we're going to add. And then what? Now you have to add it to the splay tree. Okay. So splay s node equals new splay. So the index will be side length 1 times side length 1 plus rightmost command. I guess just rightmost command will be the value. And then splay nodes at command or at side length times side length plus rightmost command times 2 equals s node 1. Okay. So then point P1 equals new point, command to add at 0, command to add at 1, P1A, P2, I guess this will just be, okay, so 2 and 3, and P3 and P4, we've got these as well. Okay, so this will be P1, or this will be rotate P1 width and height. Oh, this is just side length. Okay, cool. Okay, so S node 1 dot, oh, we need to union these. Link. Okay, S node 1 with P1 dot to S. The side length will be this, the display nodes, yes. Okay, and link this with P2, and then link the other edge with, we're gonna link this with P3 to P4. Yeah, okay, so link this up. Oh, darn it. We need to do this safely. Okay, display end1 equals this. End2 equals this. So if end1 dot, or if, what's the method name called? Find root. So find root of end1 equals find root of end2. Then we need to find the smallest on the path and remove it. Okay. Yeah. Okay, so int min equals path aggregate from end1 to end2. Path aggregate. What's wrong with path aggregate? Oh, we need to find root. Okay. Yeah, so what is this? So this is make root, yeah. Okay, so this will get the command we need to remove. So now we need to remove command edges from min. Oh, wait. We need to remove a bunch of them. All the way up to min, yeah. Okay, so while leftmost command is less than or equal to min, remove command edges leftmost command plus plus. Okay. So we've got these things, and then we have Oh, we also probably need the command. Command number. Okay, so then we have display S1. What do I call it? Yeah, S node 1 will be display nodes at side length times side length plus command num times 2. Okay, and then we want to cut S node 1 All right, keep doing this until we remove it. So this is the thing we have to remove. Oh, wait. Is this really it, though? This isn't true. Yeah, I needed to think about this more. We can't just like remove the edges here because, I mean, for a couple of reasons. First of all, this first splay node and second splay node can conflict with each other. So it's like not totally legit. We need like another abstraction here that basically just does like dynamic minimum spanning tree with predefined edges. Like when you know when things are going to be removed. Yeah. Okay, so let's try again. So we need MST of all of the edges. Yeah, and then we need to see like, okay, so then we have like, are these connected? We need add edge, and then we need remove first edge. This is not the right way of doing it. Okay. Yeah. Okay. Not enough time to get this. Unfortunate. Oh my goodness, so popular. Maybe I have t-shirt work to do. I guess let's talk about solution ideas to everything but F, since I can't finish implementing it in time. Yeah, that's fine. All right. Sounds good. Yeah, solution idea time. Okay. Let's close this out. Yeah, so I guess here's my contest. I got A, B, C, and E. So not great. I know how to do F, didn't finish implementing it, and don't know how to do D. So the solutions to A, B, C, E, and F. And then if the editorial comes out right away, then I'll read how to do D. Otherwise, I guess you're just left to your own devices on that one. Okay, problem A, not shading. So yeah, there are a couple observations here, but basically the problem is you have a grid of black and white cells, and you can either shade an entire column black or an entire row black if there's at least one square in that column or row that is already black. And the question is, how many turns do you need to shade a particular cell black if you're given the starting grid and which cell you want to turn black? So the key observation here is that since when you shade an entire row black, you shade all of the columns black, right? So if you do one row operation, then you can do any column operation you want. So as an example, if we have, I mean, this is pretty obvious, I guess, but let's say we've got this is our grid. If we want to shade this element here, like this O or this O here, if we want to shade that black, we can first shade this entire column black, and then we can shade the bottom row black, and now we'll get it. So you can always do it in 2 elements as long as there's at least one starting position that's shaded. You might be able to do it in 0 elements if it's already shaded. So if so, then you just print 0. Otherwise, you might be able to do it in 1 turn, and that would be if you have something in that row or column that's already black. So you just check for that. Otherwise, if there's anything on the board that's shaded, you can do it in 2 turns. Otherwise, it's impossible. So you just kind of have to casework it out. Not too bad, but still a fairly straightforward problem, I'd say. Okay, that's problem A. The solution to problem B is a little bit less obvious, but still pretty straightforward. So in this problem, you have a creepy guy and a girl, and the girl is going to paint a bunch of seats pink. In other words, the girl's going to prevent the guy from sitting in some seats. The girl wants to stay as far away from the guy, but the guy, who's creepy, wants to get as close as possible to the girl. Now, the question is, assuming both players play optimally, as in the girl chooses her seats to paint optimally and the guy chooses the optimal seat to sit in, and then after the guy sits, the girl sits farthest away from him, how close will the 2 people be? There's an important part of the problem, which I think I should mention, which is in this case here, so let's say these 3 seats have been painted pink, and then Raul would choose to sit in this seat, Tina would choose this seat. The distance between them is the Manhattan distance, so it's right 1, up 1, up 1. So the distance is 4 apart. However, like the thing to notice here is the distance does not ignore the pink spaces, right? So the distance can travel across pink squares, even though Raul can't sit in pink squares, like him traveling to Tina, he can walk through them. So yeah, that's the question. Okay, so the first strategy is like, Raul's moving first. So let's say it's Raul's turn, and there's some seats he can sit in. Which one will he sit in? Turns out he knows Tina will sit in whichever seat is farthest away from him. So Raul is going to sit in the seat that is closest. Those are always going to be the 4 corners, just because of the way Manhattan distance works, right? It's like a diamond that expands out from you. So an expanding diamond will hit one of the corners last. So yeah, you only have to check the 4 corners, but for each square, Raul knows like how good it is. And the quality of a square is just its distance to the farthest corner. So the squares in the middle are going to be best, and the squares along the corners are going to be the worst. because it'll be farthest away from the diagonally opposite corner. So, to be clear, I don't think this is mentioned, but Tina is allowed to sit in the pink seats. Yeah, Raul isn't. So, okay, so Raul knows which seats are better than others. And in particular, the score of a seat is its distance to the farthest corner. So, in this example, these middle two spaces would have score, like this has a score of 3, this has a score of 3. The spaces that border that all have scores of 4. So like the one Raul is in now has a score of 4. Also these ones on the top and bottom have a score of 4. And then the corners all have a score of 5 because you have to go right, right, up, up, up to reach the opposite one. So yeah, that's the idea. Raul's going to sit in whichever seat is best that isn't painted pink. So now it's Tina's turn. So Tina has to decide, okay, which seats is Tina going to paint pink? If Tina wants Raul's score to be as big as possible, right? Raul wants the score to be as small as possible. Tina wants it to be as big as possible. So which ones does Tina paint? Well, obviously Tina just paints the best choices that Raul has. So Tina's going to start with the middle squares, and then she'll expand outwards from there. But it doesn't really even matter where they are on the map. We just care about what is what's the minimum possible score that Raul can get that Tina hasn't like crossed off with pink paint. So yeah, we can just like make a list of all of the choices Raul has. Here I just iterate through every square, and for each square I calculate its score. So it's whichever corner is farthest apart, farthest away from it. And then when it's Tina's turn, initially if Tina has no buckets of paint, Raul will get the best score. That's going to be the smallest thing in the priority queue. Otherwise, if Tina has one bucket of paint, she'll paint that worst score, and then Raul will get the next best thing. So we'll remove that first thing, and the next time we go through this loop, we want the first thing in the loop. So yeah, this is the solution to it. It's very straightforward, very simple, but it's a little bit more difficult to understand exactly what's going on here, which is why I think this is a good problem. I really liked problem B. Problem A was kind of whatever. Problem B was very good. And then things kind of went downhill from there. Not in my performance, just the problem quality just. Okay, problem C. Yeah, so this was, I don't know, whatever, not terrible, I guess. Uses twin primes, so kind of fun. You know what I should have done? Did they have a limit on how big these things can be? They do, darn. Because Jenny's phone number, 8675309, 86753, it's a twin prime. 8675311 is also prime. Also 10 to the 9th plus 7 is prime, so fun fact of the day. Okay, for problem C, there's a twin prime. Of course it's prime. Everyone knows it's prime, but it's a twin prime. For problem C, not assigning, you've got a tree. You want to give every edge a certain weight so that both every edge has a prime weight and also every pair of edges that are adjacent by some node will have a sum of weights that's prime. So the first thing you should immediately think of when it comes to prime numbers and having to assign things that are always prime is everything, like we have to watch out for even numbers, right? So if you have two adjacent even numbers, it's going to be impossible. Similarly, if you have two adjacent odd numbers that aren't both 1, well, if they're both prime, they're not going to be both 1 because 1 isn't prime. But if you have two adjacent odd numbers that aren't both 1, those will sum to an even number, which won't be prime. So the only even prime is 2, and there are lots of odd primes, but no two odd primes added together will be an even prime. Which means the only way this can work is if you have a chain of numbers where it goes twin prime, lower of a twin prime, like 3, and then a 2, and then lower of a twin prime, and then 2, lower of a twin prime, and 2, or vice versa. You can start with the 2, and that works too. But it's got to be a chain, and it has to alternate between the number 2 and the lower of a twin prime. So another example would be like 2, 5, 2, 3, 2, 5, 2, 3, right? Because 5 is I guess a double twin prime, triplet prime. It's got a 3 and a 7 that are both two numbers adjacent to it and prime. That's pretty cool. Yeah, that's the idea. So why can you not have a group of 3? Well, let me show you. If you ever have an intersection with 3 elements like this, if you ever have something like this, what happens is one of these first two, one's got to be even, one's got to be odd. So let's say this is a 2, and let's say this is a 3. So far we're okay with this path, right? Because this has to sum to 5, so that's fine. The question is, what is this going to be? Well, it can't be a 2, right? If it's a 2, then these two sum to 4, which is even and not prime, so that doesn't work. It also can't be odd. If it's a 3, right? Then this will work. This will be 5 as well, but now we have 2 odd numbers that are adjacent, so that's not going to work. So you can't ever have a node like this that has a degree bigger than 2, because it's just not possible. Yeah, so that means the only other types of graphs that are possible are ropes. Looks like this. And these are easy. You just do 2, 3, 2, and then you're set. Okay, that's the idea to problem C. Let's talk about problem D. Nope, JK, I don't know how to do problem D. Yeah, I don't know. Sorry. Apparently it's pretty easy. I didn't figure it out. Can't tell you. Problem E. Problem E is a horrendously bad problem. So uninteresting. I don't know how it got approved for the set, but it's just super boring. It's also really easy. Yeah, so it's literally just a Dijkstra's. You just do Dijkstra's. Like, I guess you have the kind of annoying part here, which is that like this grid is technically very large. So technically it's like 10 to the 4 by 10 to the 4. So you can't actually make all of the spaces, but you know, that's not really a problem, of course, because you just coordinate compress. So you're given this really big grid, but you can ignore most of the spaces. So if you have a ladder that goes like this, maybe, and that's, or maybe you have another ladder over here that goes like this, and then you have a third ladder that goes like this. In that case, you can just ignore all of the spaces that don't have the start or end of a ladder and aren't the start or end of the grid. So only the spaces I've circled are the ones that actually matter. Yeah, and then you can just do your Dijkstra's on that. So in particular, the edges that you'd actually add here are you'd add a bidirectional edge this way. You have a one-way edge here. You have a bidirectional edge here. A bidirectional edge here. And then you have bidirectional edges here. So since you have order n ladders, you're only going to have order n plus, you're going to have order m or order n edges as well, because each ladder will add at most 3 edges. So you'll have this edge here, or maybe it adds like at least, yeah, it adds at least 3 edges. So you had an edge going here before. Now you've just turned it into 2 edges, and then you had one going here before, so you add 2 more edges. So every ladder adds 3 edges, worst case. So you have not too many edges in total. Okay, so there's one other part of the problem which is left, and that is you can't run Dijkstra's when you have negative edge weights. And the reason for that is because you can find, the way Dijkstra's works is it looks at like the best place you can come from. And it says this is the best, like this is the place with the shortest distance, which means if you go to any of the other spaces first and then try and come here, you can't do better than what you've already done, because all of the other things have a distance that's at least as big as this. So if you spend that much distance and you assume there are no edge weights that are negative, we can't improve on this at all. So we don't need to worry about any of the other paths. We can just evaluate this path immediately. In this problem, all of the ladders can have negative edge weights. So that's not necessarily true. You can't just do normal Dijkstra's. However, they kind of give the solution away very clearly, which is they say that all of the ladders go up. So since the ladders are always going upwards, that means you know what order you can evaluate the Dijkstra's on. You know you can evaluate it from lower to higher. And when you do it like that, then you don't have to worry about having these weird cycles, because within a certain layer, basically you're just doing the Dijkstra's layer by layer, right? You're doing a different Dijkstra's on each level. So when you do it like that, you don't have to worry about like negative edges, because they're not going to matter at all. So they don't break the Dijkstra's in that case. So I guess it does teach something kind of new, but overall, I just I don't think it's a good problem. I think there are these random restrictions, right? Ladders don't seem like they would be one-way tools, first of all. You can climb down a ladder, right? So the flavor text doesn't make sense. And additionally, you're running through walls and that has a cost, it doesn't make sense. And then additionally, you're printing no escape, which I guess maybe is understandable because -1 is a possible answer, but still, there are just so many problems with this. It's just not a good problem. And also, it's just easy. I just saw it right away. I didn't feel smart when I solved it. It was just easy and annoying. So, okay, yeah, that's it. I don't like problem E. Not a fan. Anyway, problem F was cool though. So let's move on to problem E, or to problem F. Okay, problem F. So yeah, in problem F, you have this grid, and you want to make two congruent pieces. So two pieces are congruent if you can translate or rotate or reflect them onto each other. And we'll talk about that in just a minute here. But I think we'll talk about it in just a minute. I might be slightly wrong with my proof, but yeah, I think we're good there. So the question is, there are a bunch of these times we're going to glue two pieces together, and these are going to be two pieces that are adjacent in the original drawing, and we want to know if it's still possible to make to cut this into two separate pieces that are congruent in some way. So in this example, they have two Fs, right? And you can take this bottom F and rotate it 180 degrees to get the top F. And that's the only way that these two are congruent. But you can notice that we can cut these along the path that we're given, and it doesn't cut through any of the two glued together squares. So that's one problem. The sub-problem is if we were to give you all of these lists of squares to glue together, and we told you to glue along those, then the question is can you cut it in some way that it's congruent? But the problem is really actually harder than that. What the real problem is it says, given these list of commands of adjacent things which you should glue together, what is the maximal size of this list that you can take such that for this maximal subarray, you can glue the entire thing together and it still works? Which is a slightly more difficult problem. So yeah, to handle that part, you need some data structures at least. But let's talk about the original problem first. Here's the idea. So if you've got one of these grids, right? Let's say you want to reflect one thing to be another. Let's say you're going to do a vertical reflection here. You know this top element is going to be in one part. And when you reflect it, you want the other thing to be part of the bottom piece, right? So this will be white, the top one will be black. There's going to be some point where they split. And this point has to be in the middle. Because if it's not, when you reflect it, you won't get something that's congruent. So this has to be in the middle. And similarly, this is going to be true for all of the coordinates here if you're flipping like this, which means you're literally just going to have two rectangles. I'm pretty sure there's just no other way of doing it if you're doing this kind of reflection. So yeah, there's not really any benefit in doing a reflection like this, and you can make the same argument for a horizontal reflection. So reflections are kind of useless here because these two elements, sure, one's a reflection of the other, but also you can, this is also just a rotation, right? So if you just rotate this box 180 degrees, you get the same thing. So the congruent argument is really just one's a 180 degree rotation of the other, once you figure that out. Another thing which is, I thought, helpful, but maybe not necessarily 100% required to understand to solve the problem, but I still thought it was useful, is if you've got your square like this, you can't ever have one group have this corner, and this corner. Like you can't have one group have any 3 of the 4 corners, because if you do, there's just no way to place another thing like this that doesn't overlap the first thing. So since every corner has to be part of at least one group, you know you need to have like this corner as one group and this corner as another group. And then additionally, you need a corner here and a corner here. Like this. So this is one way of doing it. The other way is to have like A, and B, and then have them kind of split like this. Now this line doesn't have to be straight, right? You can have some complicated thing like this where it rotates, but the corners have to be divided in this way. You might ask, why can't you have the diagonals like this? Maybe this is obvious, I don't know, but the reason is because these 2 pieces need to be somehow connected, which means there's no way for these 2 A pieces to be connected because they would overlap on some space. So there's like, you can use the intermediate value theorem, I think, to prove this. But yeah, you can like consider the highest and lowest A and B at each x coordinate and show that they'll cross each other at some point, which is where they'll both, at a certain x, they'll both have the same y, which isn't allowed because they have to be disjoint. Okay, so there's that. So now the question is like, how do we check whether this is going to be possible? Sorry about the old writing here. Okay, so here's the idea. Basically, we want to know, is this corner going to be connected with the top if we make the unions for both sides? So in other words, we know at this point that we're going to do a 180-degree rotation, which is the same as a horizontal flip and a vertical flip. So we know like what it's going to end up looking like, which means if we do some union like this, if we union these 2 pieces here and here, we can also union these 2 pieces. And we can keep doing this until these top left and bottom right end up being connected together. At that point, we know, okay, we've done something illegal. We have to start undoing moves. And that's just what we're going to do. So we're going to go through our array, keep doing as many moves as we can. And then once we see, oh, we've accidentally connected the top left and the bottom right, then we have to keep undoing moves from the beginning. So now all that we have left is like, how do we have some data structure where we can repeatedly do another move, erase a move from the beginning, and check whether the top left and bottom right are connected. Those are the 3 operations that we've got. So this is like kind of like a disjoint set, but it's like a disjoint set Q sort of thing. It's a bit tricky. And it turns out you can do this with a link cut tree. So the idea is you have one node for each of these nodes on the grid. So each of these 16 nodes has a tree node. And link cut trees support operations of you can connect 2 nodes together as long as you keep a tree. You can't ever have a graph, but or you can't ever have cycles. But you can connect 2 nodes together with an edge. And these edges can have weights or whatever. Well, usually the edges don't have weights. Usually the nodes have weights. But you can just like make a node in the middle of the edge. So you do this, and then with your link cut tree, you can store along some edge path what is the smallest value on this edge path. In particular, the smallest value will be what is the first edge along this path that was made. So the edge value will be when it was made, and then you want to know what's the earliest edge along this path. And that's the one that has to be deleted. So your leftmost query has to be after that node. So that's the idea. We're going to store this link cut tree where the tree that we store is the maximal spanning tree of the things we're interested in. So yeah, let me try and explain this one more time. So let's say we've got, like, first we have this edge here, like this is 1. Then we have this edge here, which is 2. Now maybe we're considering adding this edge here, but a second time. So obviously, well, okay, maybe we're considering adding this 2 edge again instead. So while we're adding this 2 edge, if we did, it would connect this node and this node. So we obviously can't add both of those edges. So we have to delete this edge here. So we'll unadd it. And now we'll be able to add this edge. Then we consider adding this edge 3, that's fine. And then we're considering adding this edge, but we can't do it because it would connect the top left to the bottom right. So yeah, we erase edges 2 and edges 3 until we can do that. That's one way of doing it. You also have to watch out for cycles as well. So cycles obviously won't change the connectivity of your link cut tree. So if you have a cycle, like, it's kind of fine to just ignore. You can just remove the smallest edge in that cycle because that'll be the first node that gets removed anyway. And then when you're doing these queries, although I said like remove, you don't actually have to remove them from the link cut tree. You can keep them in the link cut tree, but just store like what's the minimum thing in that cycle, and then keep removing it as long as there is a cycle, I guess. So maybe it is just easier to remove it. Yeah. So I guess that's a bit messy. There might be a way of doing this with like some segment tree, but I'm not particularly familiar with how that would work. And link cut trees certainly are a possible way of doing it. I was pretty close. I think I needed maybe another like 20 more minutes in order to come up with a solid solution, and if there was any debugging to finish that. But yeah, I was pretty close on it. Anyway, that is Codeforces round 766. I hope you enjoyed. I thought it was a good contest, except problem E was super boring. But other than that, I thought it was pretty good. Thank you for watching. Hope you have a great day and a great weekend, and I'll see you on the next one. Goodbye.